pests or some diseases, or how to adapt to some weather conditions so that we may be growing a particular type of seed in a given region. So in general, precision agriculture, by being precise and efficient, it will assist us in what you call the optimization and also data-driven decisions. You see, this cartoon is just trying to show these two, say, ladies. They have some sickles. They're coming from the farm. I say they may get a decision sometimes given that they are using precision agriculture. I'll give you some examples, I say, shortly about how this, I say, work out. So what should be delivered when we talk about, say, smart farming? Normally, to a farmer, useful information may include the optimal time to plant. By using precision agriculture, we can advise a farmer to know the best time to plant a particular type of seed. So this is what I've just said. You know, different types of seeds may have different durations for them to reach their maturity. So by deploying precision agriculture, we should be able to advise the farmer to understand this better. Crop performance. In addition to that, a farmer can monitor crop performance using precision farming. Potential threats to crops, for example, climate change, maybe flash floods, heavy rainfall, all these can be sorted out using precision farming. Existing threats to production. Imagine there's some locusts in a given area. A farmer may know this and get some precautions on how to, say, avoid or protect from such threats. So it may not only be pests, even diseases or some harsh weather. Say these solutions can also be provided by what you call precision farming. Say temperature also, in terms of say temperature variability, this information may also be important to a farmer say who is maybe concentrating on a particular type of crop. Rainfall variability and also availability, that is also another information which is very important to a farmer. A farmer should know when to expect rain. So, you know, we are in different say geographical locations. Different geographical locations receive the rainfall in different time. So if we are using precision farming, it is very important to understand such information. Again, soil moisture information is another set of data which is important to a farmer. We may have precision farming which solely say targeting on soil moisture. We are giving information to say a farmer regarding soil moisture. A farmer may know when to plant say based on what is already existing in the soil regarding the moisture. Not only that, crop suitability, some crops may do better in a given type of soil. So different locations, again, have different spatial say locations, which are also qualified for different say types of seeds or different types of crops. Some crops may do better in clay, other crops may do better in sand, say, or raw soil. It depends on the crops themselves. So potential crop yield is also another aspect which is necessary to a farmer. This information is important to a farmer. We may also provide the farmer this information that, okay, if you grow this, how much will you say yield by the end of the season? That information may be say achieved through smart agriculture. So in addition to farmers, what information should we give to policy makers? Which information is necessary to decision makers? So decision makers, on the other hand, may also need crop performance information so that they may use this one for their reports, say regarding how different countries or different locations of a country are performing, or how to expect, say, the as a given potential yield of, say, a particular type of crop in a particular county. Not only that, potential threats to crop as a field, just similar to the previous slide. Existing threats to production, also similar to the previous slide. But important to policymakers is when to intervene if there is a challenge in terms of agriculture. They should know exactly when they're supposed to assist. Imagine we have advised them that since we had a drought or we have locusts, then you politicians, you have to assist. You have to feed some people in some locations. So they should know when to intervene. So what it means here is that we may come up with a model which can advise politicians the best time for them to intervene. So we may also advise them how to intervene when a problem arises. So apart from that, they also need crop suitability information, and also how the suitability will change. So we may say, okay, if we plant corn in this particular area, it will do good. We can't just tell a politician that information. Why? Because weather may change, and the stability of a particular type of crop may be affected. So it is very important to advise them how suitability may change. And also potential crop yield, I say, is a very important information which should be given to these policy makers. And lastly, on this slide, the policy assessment. Say they have a policy on agriculture, for example, or they have some guidelines which they use in managing a particular aspect within agriculture. So if they see some challenges, they now have to compare with they have in their policy. This may, in the very end, assist them to assess if they are doing better, or if the Ministry of Agriculture, for example, is doing better or not. And this may, in the very end, assist in, say, maybe updating their policies to cater for some issues which were overlooked. So, soil moisture data sources. Soil moisture data sources. For soil moisture estimation at a low scale level, which is also very important for validation. I repeat this slide from, the previous presentation in, RCRMD, that we may use infrared thermography in estimating soil moisture. We may use soil moisture sensors, gravimeters, gypsum blocks, dielectric probes, time domain reflectometry, Newton probe, and of course, tensiometers. So these are different based on how they are deployed, as I've showed you in this slide here, that the moisture sensors apply the electrical properties, the gravimeters just a matter of drying and weighing the soil, gypsum blocks depends on the resistance of the soil, dielectric probes, we measure the constant. In the time domain, we are using the pulses or the electromagnetic signals to determine the moisture. The neutron probe, we are using the hydrogen content in the soil. In the tensiometers, we are measuring the plant suction, how much water are the plants absorbing from the soil. In the infrared thermography, we are basing on surface temperature differences. So these are just for validation purposes or small scale methods for correcting soil moisture. Maybe TASAM, of course. We'll see other methods which are also applicable in soil moisture application. So here I have soil mapping missions. So one of the most used soil mapping missions is what we call soil moisture active passive. So this is simply an airborne system which applies some sensors on board which in turn assists in as a grabbing or grasping soil moisture in a given particular location. Apart from that one, we also have soil moisture and ocean salinity. We also have Centero one, we have Aquarius. Of course, the soil moisture active passive is simply called SMAP, and this one is simply called the SMOS. Apart from that one, we also have Global Change Observation Mission Water. We also have, this is abbreviated as the GCOMW. We also have Advanced Land Observing Satellite, which is also simply called the ALOS. And we also have, this one, which is the SACOM, is also another as a satellite system, which is specifically used for mapping soil moisture. So it depends on the user and also the data availability. Sorry. Hello? Hello?
Yes, Robert, we can hear
Okay,
you.
yeah, okay, I heard like some noise. I thought somebody is using like a phone. Okay, should I proceed?
Yes, please.
Okay. So these are just some examples. It depends on the availability of the data in the user. The user may choose which. Yeah, there's some noise in the background. Yeah, so the user may choose which one to use or may combine data from different sources in developing a machine learning model. So we may also we also have some more like NASA ISRO synthetic aperture radar, which is also very useful in providing soil moisture data. This is simply called the NISAR. So all those are very important in giving geospatial scientists some data, which is very important in developing models or for using in terms of data analysis regarding soil moisture. So precision agriculture monitoring. What do we do in precision agriculture monitoring? So we normally use some in-situ sensors like those which I presented in say 3 slides before this about how we grab soil moisture data from the soil. Those are also useful. We also use satellite imagery, and we may also deploy what we call machine vision. I will show you what we do in machine vision very shortly. So in terms of sensors, we may have like spectra radiometer, or we may have a sensor mounted on an unmanned aerial vehicle, which is specifically for thermal imaging. Yeah, we may also directly have some satellite imagery, not satellite imagery, UAV imagery grabbed by the drone itself on a particular location. And in terms of machine vision, we may monitor directly in the field using a robot. So we may have a robot which is using a GPS or a GNSS sensor in addition to other sensors like LiDAR. So the GPS itself will be just for real-time calculation of the position. The other sensors is for object detection. For this robot not to maybe damage the maize itself in this field, we may use the LiDAR and apply some algorithms for object detection. All that information used together is important in, for example, crop health monitoring. So in addition to these, we may also have what we call multispectral remote sensing, and of course, the hyperspectral remote sensing. Of course, some of these multispectral and the hyperspectral may be deployed maybe using a helicopter or using as like huge UAVs, yeah, to collect data at a given resolution for a particular area. So all in all, it depends on, I say, the objective behind a given project. So agriculture mechanization in terms of support equipment. I say in agriculture, we may also use tractors where we, I say, have an onboard software. Here, I just have an example, which is the Black Boss Marine Soil Mapping Kit. This is just for mapping soil, but it is used in an agriculture machine, as a, for example, a tractor or grader, as a, which is directly applying machine vision algorithms in mapping the soil as it is as a being driven within a given farm. We also have another example, for example, 3R as a tablet VT box, which is as a telematics directly using as a satellite, as a also for mapping soil moisture. We may also have some auto steering as algorithms applied to some machines used in agriculture for doing some mapping like slope, and also for soil sampling. We may also have some board for controlling the planting of seeds. Yeah, this is also mechanization. So in controlling the planting of seeds, we are doing multiple things. We are using a geographical positioning system. We are using as a GPS sensor on board for real-time kinematic calculation of a given position. Then we are directly applying an algorithm to calculate the position where to drop a seed. So as the machine is hovering in the farm, it is determining the optimal position to drop a seed. So in turn, we are not using humans apart from the operator. Despite that some of them may be autonomous, we may also have some which are manned. So in both cases, what is important is that the either soil mapping itself or planting itself is mechanically done using such type of machine. So there are some systems, for example, for grade control. This is just trying to control the topography to allow water to move from a certain grade to a particular grade. This will assist farmers to know where to store water, maybe using some box leaches in a given farm. Of course, we may also have some auto steering system. Yeah, that is also very, very important in controlling some operations like seeding or fertilizer application in a given farm. So all these systems are important in providing data to a farmer or in assisting a farmer in real time. So apart from assisting a farmer in real time, we may also have the data for post-processing purposes. I will show you which data is necessary for post-processing purposes, which is very important for crop health monitoring. So precision farming through machine learning. So what should we do for us to deploy machine learning? So here I have to emphasize that the systems I presented in the previous slides are also using artificial intelligence algorithms to operate. So machine learning is part of the artificial intelligence algorithm, which I want to give you here as an example in as a smart agriculture. So here, what is the main impact of machine learning in smart farming? So as I said earlier on, it makes agriculture more efficient and effective. So the question is, what is the relationship between precision agriculture and, of course, the machine learning? So here, despite that, precision agriculture may include both hardware and software. Machine learning here, as may be described in terms of the algorithm part of it. So in all, I said both systems will depend on data gathering, processing, and of course data analysis. So in terms of the technology which is important in these systems, we may have autonomous vehicles, we may have GPS-based soil mapping or soil sampling, and of course the automated hardware. So what I mean here is that you may design a hardware, a certain system, which you now incorporate a certain software to perform a different task on a farm. So we may have telematics software or sensors in addition to, say, the three mentioned here. So in addition to this, you can also have a camera. So you can have a camera mounted, for example, in a UAV to capture the images. In addition to the inbuilt camera on the UAV, you can take a different camera to perform some additional tasks as you are correcting the images. So in addition to this, you may also have, say, robots, drones, as I've already said, say some control systems, and of course the GPS guiders. I say all these systems joined together, I say they make precision agriculture and the what we call ML, or I say artificial intelligence as a whole. So what are the main solutions? I say the machine learning solutions in precision agriculture. So in general, data sets can be learned or can be trained to achieve different use cases, and which may give out, for example, soil crop and the water functions. So in terms of soil monitoring, we may have it for soil sensitivity, moisture prediction, organic carbon prediction, pesticides and fertilizers, insect detection, and of course the fertility prediction of the soil. In addition to soil monitoring, we may also have crop monitoring in terms of disease detection, crop recognition, selective breeding, yield prediction, weed detection, and of course the grading by quality. In terms of water, we may have weather prediction, weather monitoring, irrigation system, water usage prediction, leak detection, and of course the soil water monitoring. So these are some examples of the ML solutions applied in precision in agriculture. So here I have to emphasize that it depends on the form. It may be a software or like embedded software, or like a software itself, or like implemented in a particular equipment. So it may be either hardware or as a software alone. So here I just have, for example, the mean rainfall in millimeters for some years from 1984 up to 2022 as just an example of some of the data we may need to assist the modeling. We'll see shortly how we can do this. So let me give you some examples of machine learning algorithms which are used in precision agriculture. So we may have what you call predictive analytics. This is, I'd say, one of the algorithms which we apply and is important in helping farmers to better predict crop yield. It also assists in forecasting demand for specific crops, optimizing irrigation and the fertilizer usage. Also, it also assists farmers to know when to plant, how to care for some crops. Price projection, say you have grown some groundnut, how can you project the price? Say using predictive analytics, yeah, it's possible. So of course, the early warning signs, we also say we should also be able to say get this information from predictive analytics. We can also identify pests and diseases using predictive analytics. So just like predictive analytics, all these functions can also be achieved by what you call computer vision, can also be achieved by what you call computer vision. Not only that, it can also be achieved by, say, deep learning. So in addition to this, say deep learning as an artificial neural network may also assist farmers to develop new varieties of crops. Yeah, it depends on how the model is initially trained, or what input parameters are included in order to come up with the new varieties of crops. So that is the advanced programming in this aspect. So in addition to this, what else? What are some of the examples which may also be used, or what are the specific machine learning examples which may also be used? So here I give you some common ML models. For example, the Bayesian model. So in terms of the Bayesian model, I say we may have climate and weather data set. So like temperature, precipitation data, humidity levels, solar radiation, wind speed and direction, frost occurrence and duration, growing degree days. In addition to climate weather, we may also have soil characteristics in training a model using a Bayesian approach. We may have soil type, soil pH level, soil moisture content, soil organic matter content, nutrient level. In addition to that, we may also need crop information like crop type, planting date, harvest date, crop variety, initial crop density or planting density, crop health. All this information may be used in training our Bayesian model. In addition to that, we may also have the agronomic practices. For example, irrigation frequency, if we are undertaking an irrigation scheme, fertilizer application rate, pesticide and the herbicide usage information, or crop rotation history. So all this information is very important in, training models. Apart from the Bayesian model, even most of the regression models, we may use this, even the clustering model. I'll show you an example of a clustering model. For example, we may use clustering model to classify some different types of seeds. We group similar seeds together according to their similarities, or we put them apart according to their differences. We may deploy the clustering model, or we may use directly the artificial neural network models using all these type of data set like the climate, soil, crop, and the agronomic practices. So here, I say all this information is very, very important in training different types of models, which are commonly used in precision agriculture. So what else in addition to this? So we may also have geographical data. For example, elevation, slope and aspect, soil depth, and of course, the proximity to water bodies. Yes, if we want to know something like maybe runoff or maybe soil erosion, yeah, we may use additional information as a geographical. Apart from that, we may also need the historical yield data, to just know how much farmers have been gaining from their farms. Yes, this will assist in projecting how much they should expect in a particular season. So we may have previous year's crop yield for the same field or location, and we may have time series in the past year as a yield. That information is important as input into our model, whether using Bayesian regression, clustering, or artificial neural network models. So we may also have crop growth models, for example, parameters related to crop growth stages, or maybe photosynthesis efficiency, or biomass accumulation. It depends on the need or what you want to achieve by the end of the day from your model. So we may also have some remote sensing data like satellite imagery for vegetation health assessment, or maybe NDVI, or say thermal imagery for crop stress detection. Crop rotation history. This information is also important as input into our model in order to come up with a very powerful model to achieve a given goal. So this information is crucial in training different types of models. It depends on what you want to input in a given model for you to come up with the best solution. So let me give you a simple example here using Sentiero 2. I have this Sentiero 2 data for a given area. Then I apply binarization, classification. In other words, I split the image into ones and zeros, where ones and zeros shall mean a different parameter in that given image. In this case, I have split this one. I've labeled this one into crop and non-crop. Then in the very end, using this binary classification, for example, using semantic segmentation algorithm, I should be able to come up with this output, of which the different color codes here shall mean different types of seeds like soya, sweet corn, or alfalfa. So this is just one example using remote sensing data like Sentiero 2. So in addition to that, in case you want to know the prices, you want to project the prices using a given model, you may also need the crop prices. You may also need the market demand and supply dynamics in your country or in a given area. And you may also need to have the input costs. These are the labor charges in general. For example, you have got an estate. You know how much you have spent on fertilizer. You know how much you have spent on labor. You know how much you have spent on water if you are doing irrigation. You have to take all those into account for you to make a very good projection regarding, the market. So in terms of the disease and pest data, you may also need to have occurrence and severity of specific diseases and pests. You may also need to have information regarding the pest control measures. So all this information is important depending on the outcome or depending on what you want to have by the end of the day. Again, management practices are important in training a different model or a particular model. I say you may have crop rotation strategy. What strategy did you use? For example, you planted the corn this year. You plant maybe legume the other year. You plant tobacco the other year. So that system, how do you distinguish it from a certain parcel where you used a different rotation strategy? Or did you skip a particular year without growing anything? Then you go ahead in a different year to grow a different particular type of seed. In addition to that, what were the tillage practices? Were you using a tractor, or were you using, say, horse manually, using people, or say to do that work directly in your farm? So all those, aspects should be taken into account in the model you are, developing in order to come up with the perfect solution. So in terms of, the dashboard and the quality metrics, what is the precision agriculture, or how can we deploy precision agriculture using a dashboard or different dashboards? What are the main quality metrics? So what you may check when you want to, develop a dashboard to achieve a certain aspect, you may think about the quality of the input data set. For example, you may have precipitation data for different years. Here I have precipitation data from 1982 to 2023. And of course, here I've also shown you as the temperature data on the same, as the time series, the variation between temperature and the precipitation. As you know, these are related. When temperatures are higher, we may expect evaporation from the ground. So this is in general, we are losing some water from the ground during this time. In addition to that, we may also have soil moisture data for particular years. I also have, for example, soil moisture data from 1982 to 2023. So you may check the data depending on what you want to achieve by the end of the day. Do you have data gaps in the raw data? The more the data gaps, the poorer the solution. So if you have more data gaps in your input data, you should expect to have like poor performance in your model. So if you observe some gaps in your data, you may think of updating your raw data using other sources of data, as I showed you in the previous slides. So in addition to that, how do we think of the quality of the predictions in terms of the precipitation, for example? Here I have MLP as a regressor model. I check it first of all before deploying this into a dashboard. I have to check the, for example, the correlation between the actual data and the predicted output. So in addition to using the regressor, I can check, okay, how other machine learning models perform using the same data set. So I may check against the different machine learning models. For example, here I have elastic net model, I have gradient boosting model, random forest, ridge or support vector machine learning algorithms. In this plot, the different colors are just indicating the differences between the actual and the predicted. And the R, he just trying to show you the correlation between the input model and the output model. So what am I trying to tell you in this slide? What I'm trying to tell you in this slide is that before you come up with a dashboard, you should be able to know in advance that the model will perform better by doing some, initial tests. You have to know this by doing some initial tests before you publish your model into a website so that people can use it. So in terms of integrated data set, say I have disease and pest data, market and economic data, or I may have other data apart from that one. I take, say, geospatial data from Google Earth Engine. I combine this data, say, soil moisture and precipitation. So I may come up with a deep learning model, of which I say the left panel shall mean the input model, the middle shall mean the hidden layer, of which if I use hyperparameter configuration in this chart, I show you the training, the validation, and the testing. You may split it into testing, validation, and say training, maybe 85, 5, and 10%. Then this should be able to give you something as the output in the very end. So the output may be soil moisture and the temperature, depending on what you say input. So in the integrated data set here by others, I simply mean any other data you may think of to incorporate into your model to make it more powerful. So you may use, say, a very powerful machine, or you may use as a Google Colab if you don't have a powerful machine in training your deep learning model. So in this example, I'm trying to show you here. I get an example from country Malawi. So what I show you here are the COAS stations in Malawi. So I use the COAS stations in Malawi to calculate the water vapor, But what did I do here? I'm taking into account the input parameters shown in the previous slide and the elevation. So as you know that the higher we go, the cooler it becomes. I'm trying to evaluate the, say, the relationship between elevation and the amount of water vapor in the air. So the color bar here simply show you the variation in elevation in terms of, say, the geodetic stations in this map. So this is just taking one example of Nzuzu COAS in the northern region of Malawi in, say, on 11, say, September in 2020. First of all, if you're using spatial data in your model, before you publish your model, you have to know that everything is okay. Are you using a position as accurate as possible? If your interest is to get the best solution, make sure that you check that the precision of the calculated position is correct. So in this case, I assess the precision of a position, I get the biases, which are within acceptable ranges. I also try to check at 95% say error in terms of the same major and the same minor say axis of this ellipse to know how the error distribution is for a particular type of say station. So if it is a weather station, or if you want to deploy this one into a mobile app, you should be able to say make sure that that app can calculate the position, can give a farmer the correct position, so that when a farmer wants to get the moisture for a particular area in real time, it should be able to do that. And the one aspect to do that is to make sure that you can get a position maybe within 1 meter level accuracy. We may not need millimeter level accuracy in that as a type of work. So this is just in terms of the orientation of the, the axis, the shift. How has it shifted? Of course, this may not be very important to some, but it may be important to say others who are making use of the position, say making use of this one for different purposes, including navigation purposes. So this may be further classified in terms of the variation. When I checked this one, I could get the variation in terms of the elevation, between the minimum to maximum. and the variation in terms of the precipitable, say, water vapor for a particular type of, say, station. So here I have a scatter plot, which is just a geometric, which is showing a geometric relation of the calculated water vapor with respect to the latitude and the longitude. So the color bar here is trying to show you the, say, the calculated water vapor for different, say, stations. So as you know, the water vapor for different stations, that information may be important to farmers. If you are interested to advise farmers about that, then make sure that you check beforehand, or you have to check that before you implement that one into, say, a working dashboard. So water vapor, you see that decreases with increasing in elevation from this plot. And here I have, say, a station for Nsusu. Then I try to check also the delay for a particular day. I see that, yeah, the delay is okay when I check the, say, 3 sigma or the confidence interval for the estimated. So you go ahead and also verify for some different years, say how much is this model achieving in terms of the actual and the predicted. So from this one, the mean squared error is about 1.3. Yes, so this is good. I can take this one and deploy it into my model so that if I want to advise some people regarding water vapor, I can use this model. How about in terms of the differences? Yeah, these are the observed differences for the cell. So the color bar here is just trying to show you the estimated difference between the actual and the predicted. So in terms of the water vapor, so imagine you now want to come up with a map. You want to come up with a map like which should be animated. Then you have already checked that one. Then it means you incorporate your position data, you incorporate your height data, or you incorporate your assess solution. If it is water vapor, you take water vapor into account. If it is soil moisture, you take soil moisture into account. Then you may get this one as the estimated, this one as the predicted. So taking this one at the same interval from 50 to 300 mm, you may see like a slight difference in terms of the coded stations. So having reached this stage or a stage like this one, you should be able to have some confidence to say, yeah, I think my model can be as a fully implemented into as a given dashboard, depending on what you want to achieve by the end of the day. So you may use some metrics, for example, MSE, say the R or the standard deviation. So in case of this one, I got the say 0.2, 0.99, and of course the standard deviation of say about 0.5. So this shall mean that the model performance is better using these metrics. So if you get the best from your model, that's when you can think of deploying that one into a dashboard. So here I have automatic weather stations in Malawi. In the background, the different colors are the soil colors or the different types of soils as from this country. So I try to integrate the weather station data and the soil data into a different or into a particular model. What should I do, or what can I do as a given use case? So I may have a soil moisture sensor in a particular area. I may also have, say, a UAV or a helicopter where I can mount an evapotranspiration sensor. I may also, on the other hand, have an irrigation system. Then, what do I need by the end of the day for me to come up with, say, a particular dashboard or a particular system which can assist farmers in terms of, say, smart agriculture. I want to assist somebody or a certain farmer who is having an irrigation scheme using as a smart farming as a principles. So I may simply come up with an app and implement it on a smartphone. Then I have a base station which is linking the data from the UAV, the soil moisture station, and the irrigation system. Then I get this information directly into a server and link it to a mobile app. For example, everybody can use that one from a smartphone. A farmer can track when to do something in a given as a farm using a smartphone app. That is one way to do that. Or this can be done as a maybe you use different data sets. You implement such data, then you come up with a dashboard. Then it means some people interested in knowing as a what to get from a particular area can just use some queries from the as a developed dashboard, maybe publish the dashboard in a website to see maybe the type of soil in the particular area, when to grow, or the crop classification, whatever, from as a machine learning model running in the background. So do you need to know more? I think for today I can stop there, unless if you have say questions regarding this.
Okay, so
Hello.
thank you very much. Thank you very much, Robert. There are some questions which are coming up, and I would love maybe we can give this chance to Bruno so that he has several questions so that it will be very much easier for him to share with us the questions. Hi, Bruno, you can open up your mic, then you ask your question. Then after that, we are going to take over the other questions. Great. Thank you.
Thank you. Thank you, Robert. I just had a few questions. Number one, I was inquiring that in case one has very limited data,
Yeah.
which model among those 4 models that you shared, which model can best suit such a case scenario? The other question I had was on a logistics regression model applicable in precise agriculture. And the other question is about as you were sharing on the application of the course stations, or you spoke about the errors, and I was seeing a 0.03 meters error in terms of a height component. So I was inquiring, in particular, which height system were you looking at? And the last question is on the post-processing of the course data to get the PWV. Were you looking at commercial softwares or scientific softwares? Thank you very much.
Okay. Yeah. So from what you have just said regarding the model in terms of the data, in general, any machine learning model you want to train want to perform better if you have a limited data set. In other words, the more the data you have, the better the output in any model you are using. If you are using like supervised machine learning, you also have to take into account the data labeling. How good is your data in terms of the labeling? If the data labels are not precise enough, you may not expect to have a better model by the end of the day. So if you have limited data in the journal, your machine learning model want to perform better. I repeat on this point, want to perform better. Even if you check the mean square error or the correlation, you have very large values. So you may think of updating that model using other data sources. So you may upgrade the model through transfer learning. Then you check if the precision of that model has improved. I hope I've answered that first question. On the second question, you were asking about the height system. Yeah, for the height system, since we are since this presentation is simply done among participants from different countries, that one is based on the ellipsoidal. So the ellipsoidal directly calculated from the GPS as a coordinates, then transformed to Earth as a centered Earth fixed coordinate system. So that one is universal transverse as a Mercator, zone 36 degrees south, for the example I've given you, which is zone 36 south is Malawi, which is the north part of Malawi. So the height component there is a transformed value to UTM with respect to Malawi. So what it means is that if you want to calculate a position in, say, Uganda, you get a position in the UTM system for the zone in Uganda. So that is the answer to that as a question. In terms of what was the other question? Or the software. You also asked about the software. For the calculation, I used a personal Genesis software, which is called the Su Soft, where Su means Suya, soft means software. I told you I will share you this software this year anytime. I will share you this software. I know maybe you have an interest in Genesis. This is a Genesis software which I use in doing some data analysis. So it's currently not commercial. It's just a scientific software which is used for research purposes. So it is written in C, C++, and Fortran. And the automation is done using both C and the Python language. So that is that on the question on the software part of it. So all these examples for the machine learning examples are trained in Python, are trained using Python, both machine learning or the deep learning model. I hope I've answered you, Bruno.
Yes, Doctor. Yes, Robert, you've done so. Just one question about logistics model, regression models. Are they really applicable in precise agriculture?
Yeah, these are regression models. Yes, they are applicable in precision agriculture. Can you give me a specific example so that I give you a very good answer?
What I was thinking about is that about logistic regression is that we are dealing with texts. Is that
We are
you're
dealing with
asking
what?
a farmer, which crops did you grow? And then they tell you, I did this, I did this. Did it rain? Yes, no.
Okay,
So
okay.
what
Okay, no,
I thought
okay.
about.
Oh, thank you for that thinking. Yeah, what you're thinking, let me now say expand that thinking further to say open your mind in terms of this. Say you have say that type of data to say you are asking a farmer what type of crop. So you have the type of crop information, say, okay, corn, this is sorghum, this is millet, this is groundnut, for example. Then you take that information as labels. You tie that information to spatial data. You get me? For example, you have a certain farm, you approach a certain farmer, you ask this farmer, okay, where do you grow your say crops? Okay, the farmer say, okay, I have I say this farm in this county, it is maybe 0.5 acres. I grow sorghum. Then you go ahead with the questionnaire. We have questionnaire information for that one. It means your data will be both textual and will have a spatial component, which is regarding the acreage, the size of the farm. Then imagine you now take the satellite imagery or the UAV imagery of that particular area. It means you directly link the questionnaire information for labels and the UAV imagery in order to use that one as input data into your machine learning model. Hello? Hello?
Oh, yes, Robert, yes, I'm sorted. Thank you very much.
Yeah, another person?
Okay, so thank you very much, Robert. I have some few questions here, and I can see some members are also asking some questions. Okay, I will give Joseph, then I will come later. Joseph, please, you can ask your question. Open up your mic, then you ask. Thank you.
Okay, so thank you, Robert, for a nice presentation. It was so insightful. And so my question goes to the part of the remote sensing, whereby you showed us an image about the Sentinel-2, whereby you did binary classification, and later you did segmentation to identify different types of crops. So my question is this. So in the first part, you did the binary classification to identify the cropland and uncropland. And my question is like this. When doing segmentation, did you do the segmentation of the old imagery before doing binary classification, or you did binary classification and then you did the segmentation? And also, were you able to identify different types of the crops using only the Sentinel-2 imagery? Thank you.
Okay. Yeah, so yeah, thank you for that question. So for this one, I say it's just a very simple example. For the solution I showed you in terms of the soybean. Okay, let me just go to that slide. For the, here's the slide. Okay, so in this one you will see some patches. You will see some colors I say within I say the image, which I didn't show you. Those may mean others. It means I didn't pay attention to I say those features within I say the source image. So here is just the multi-class classification of the pixels into a particular number of crop types. So the general procedure here is, for example, using the say LSTM model. I take the data, for example, for 12 months time series of Sentinel-2, and I also have other satellite observation data, which I didn't show you here. Then I label them. I do the labeling. I take the crop label and the non-crop label. So in this case, I'll have the local classifier and the global classifier, which I will incorporate into the LSTM model. So in the very end, I should be able to come up with the, I say the different classifications of the seeds. I say the different classification of the crops in terms of the soybean, corn, sweet corn, or alfalfa, or the others. So here I just wanted to show you part of it. I didn't show you everything regarding this as a classification. So I forgotten the other question.
So the other question was, did you do the imagery binary classification, then you did segmentation?
Okay, you mean like repeat? I didn't get you.
Like is the first step doing the binary classification, and then after doing binary classification, you do the segmentation?
Yeah. Then
That was the question.
yeah, that's the correct procedure. That's the correct procedure. So it means here we have like a linear layer. So within the linear layer, I say we apply a different size of matrix in order to do the, I say, labels. For example, I have the locations and the labels. So within the locations and the labels, I first of all to do the image itself, to binarize the image. After doing the, I say the image binalization, after doing the image binalization, it means I'm now trying to split the image into, I say, particular numbers, or into, I say, ones and the zeros, for example, or I'm trying to take the ones as the crop, the zeros, or the zeros as the non-crop. Of course, this differs depending on the background model, I say, which somebody has used. For example, when someone uses the OC2 algorithm, the ones may be taken as the feature which you are looking for, the zeros as the feature which you are not looking for. So in the very end here, I say I get I say what you call the colors directly coded here. But here I didn't show you the mathematics behind in order to get the output result. I just show you the input and the output in general. I didn't try to show you the input and the intermediate stages within, say, this one. But it's just a simple deep learning, is a simple, semantic segmentation algorithm, which I just apply here to classify the pixels into a particular type of, say, feature, like corn, soya, or whatever, depending on what I was looking for. It means if I need like sorghum, it means when doing the binary classification, I need to define it. In other words, whatever you define in your input model, and whatever you are trying to get by the end of the day will appear. So for this user case, I just tried to get out the 4 parameters. That's why I just showed you the 4 parameters.
Okay, thank you. And then maybe one final question.
Yeah, another question. If you
Yeah,
if you are not,
question.
yeah.
So you used different types of satellite imageries, one of which was Sentinel-2, which I believe it's about resolution is about 10 meters. Maybe can you maybe I just request to know what kind of other imageries which you used, and did they have high resolution compared to Sentinel-2?
Okay, yeah, in terms of, I say, the resolution for this example, I just had the, like I said, 12, that's the 1 year data sets, for example, of Santero 2 data. I have 1 year data, I say, for Santero. Then in terms of resolution here, I consider other parameters other than the images themselves. I had to consider other parameters like the NDVI. I consider, I say, the targets or the 2D model. I also consider the 3-dimensional model. Then I incorporate my say labels for me to know what to get from say which point. So in taking the input, like for this user case, I got like 128 in terms of the input, the high resolution images, like 16. Then I had to split them into 16, 16, 16, uh, which were in the very end connected or combined in order for me to come up with say the multiple time stamps for different months for in the LSTM average. Then I take the low resolution images, I tie them to get what you call the pedestrian model. Then in the set 2, I also get the raw resolution images. I also combine them using the same 128 numbers and 16 and 64 by say combining the 16 into different sets to come up with the like 256 in the very end. So this is simply a brief of the architecture of this model. I may not explain like everything in this talk because as I didn't show you the actual procedure which I used in the very background to come up with the solution. And it may not make enough sense to just mention the numbers like 256, 16, 32, 64. It would be better if I had showed you the actual process in terms of the flowchart, how I implemented the whole algorithm to come up with the this one. So in general, I get the elevation Santero 1, like Santero 2 RGB. I mix that one in order to have a spatial resolution sensing data into a single model with some given timestamps. Then I get them, I apply the model to auto encoder for me to come up with the final solution. But if you still have more technical questions on this one, we can talk privately. I will explain step by step what I did to get this one.
Okay, thank you so much. I appreciate.
Yeah, you will contact me privately. I will explain to you step by step.
Okay, thank you.
Yeah, thank you.
Okay, thank you very much, Robert.
Yeah.
Abukar has left and he had a question, but we do appreciate. So also welcome Hema Diasin. Today you have joined a bit late, but I hope you have gotten something. Okay, so in relation to today's talk, I have a few, just a few questions. Yes, because you mentioned about the useful information that we can get, like the climate change, the pest disease monitoring, and also the rainfall, and also the moisture. Some of them, the points that you mentioned. Now, I was requesting if you could type this with the Google Earth Engine, how can we get this data? How can this be implemented? Also in connection to the machine learning models, how to build the machine learning module in the Google Earth Engine. In just a few minutes, maybe you can talk about that in connection with GE. Thank you.
Okay. Yeah. So some of the information which like meteorological data, it's possible to take that information directly from Google Earth Engine. It's just a matter of writing simple script simple script, JavaScript, to extract the data from an image. It depends. You can download the image directly to your drive, or you can extract the values from a given image. So these values may be in different say formats, but you can save that one as a CSV file or Excel file. So you can extract the time series data, for example, year, month. You specify the country you want to get the data from. You can say write a formula to calculate the average. Say for each year and each day in a month. You can say write a formula say to grab the maximum, the minimum, the standard deviation, or the percentile, say 25, 50, or 75, depending on what you want from say a particular data set. Then in the very end, you'll be able to get the data. You have, say, the soil moisture data or the precipitation data from a particular, say, source within Google Earth engine. So, depending on what you want to take from that, you can combine data from multiple sources, data for same day in a particular month. You can combine it by simply writing a very simple Python program to combine data from multiple sources into one to come up with some time series data, which you can use it later for training. So the other information which you may not, apart from the geospatial data, the other information you may not get it directly from, you may not get this data from Google Earth Engine. I gave you so many examples. For example, I say this data here, the agronomic practices. You can't get this information from, say, Google Earth Engine. Some of this information you can take from maybe the Agriculture Ministry or some maybe institutions which archive the data for some time. Because in training machine learning models, you need enough data to improve your model. As I said, to questions from Bruno, the more the data, the better the trained model output. So this other information, as I said, you may not get them from Google Earth Engine, but you can get, say, some of this information from, say, the offices. You may get some of this information from, say, the offices which are responsible for, say, archiving that type of data. But in terms of the time series, the Sentiero, 1, 2, SMAP data, all that information can be, say, downloaded through Google Earth Engine. You remember I showed you the missions, all the data from these missions, you can get all this data from Google Earth Engine. Even all this data, you can download this data from Google Earth Engine. So as I said, it's either you are taking the images or you are taking the, say, time series data, depending on the script which you write to grab some data for a particular area. So I didn't show you like one script which, or some scripts which I used in extracting data from SMAP. Say extracting data from SMAP, say from soil moisture active passive. I extracted the year, month, country, average, maximum, minimum, standard deviation, percentile, say at 25, 50, and 90. Then I combined this data with say meteorological data from NASA. I combined this with meteorological data from NASA to come up with a very powerful time series data for training the model. That is the same model which I used in coming up with, say, all these, say, even all these time series data is from the same. Here, I said here that if you have gaps, you you may not achieve as a very good model. So this was just trying to see if I get some gaps in the data, which I extract from Google Earth Engine to see if that data is good enough for training the model. So in general, from Google Earth Engine, it's just a matter of either you may deploy Python or you may deploy, say, Java to extract the time series data or to directly download the image to your drive, which you may use for training a different model for dashboard as a development. So, like I said, I still take it important to test the model before deploying it in a dashboard. That's what I stress here. So, if you check with the say some say institutions in your country, I'm not sure in terms of the availability of data in your country for updating your existing model. I'm not sure. Do you have enough, say, or some agriculture institutions which may give you data in your country, which you can use for training your model in addition to, say, remote sensing data? I don't know in your case or in your country. Hello?
Yes, Robert.
Yeah, so I was trying to check from you, do you have enough data from your, say, country, like the agriculture ministry? Can
Yeah,
you
we
get
do
some?
have. Yes, we do have some data which we can
Okay,
access. Yeah, but
okay,
at times you'll find it's not open source.
or you need to pay for that.
Yeah, you need to do some organization before you access it.
Oh, I see. So, yeah, you see what is important. For example,
Yes,
if you get some data, you may have a monthly data set. So you come up with some mosaics, then you input that data in a deep learning model, or for example, any neural network model, say fractal model. You train that one to, say, evaluate what you get from the government. Say you have some data from government bodies, or say the land survey board, whatever, for parcels. You may delineate, label the parcels which you want to take them for input. You have all your labeled data, then you include that data into your model combined with some data which you get, for example, Santia 1 or 2, you combine that data. You may use both high resolution and low resolution data into your model to see how it will perform by the end of the day. Does not necessarily mean that you have to get the best data if it is like satellite imagery data. You may combine both low and high resolution say data. So from satellite imagery, as I said, you can get the time series data. Then you can also say put this one into your model. You get some information from farmers, like Bruno's asking. You use that data for labeling. You have, say, that data for labeling into your model. So imagine the farm is also connected to some field data, which is collected by farmers. You take that data, you input into a deep learning model. By the end of the day, you come up with the cropland type, yield type, crop condition. Yeah, the crop conditions may be temperature or maybe rainfall, focus, genotype, whatever. So this would depend on the models which you use. Imagine you have some field agents in the Ministry of Agriculture who do collect data from their, say, trials. They are doing trials in different plots of crops. So they have different data. If these people can give you data free of charge, say data for crop condition, data for yield forecast. I said not yield forecast, data for crop conditions, soil conditions, disease status. You may use that data into a model to see if you can advise them about, I said, the condition of the same within a given, say, parcel, which they used as a test station for a particular asset type. So in the end, you should be able to advise the policymakers, to say, okay, I think this year will yield enough, or this year we expect nothing. So that information is what is important, I say, to get. Again, if you have that, I say, data about what you have been having in a different or in a particular country over the past years, if you can get information about like maybe drought for different years, you can also incorporate, if you had some drought information for particular years, you can take that data and also input it into the machine learning model. The most important thing of all is the architecture. Sorry, is how you, say, design your model to come up with the output. That's the most important, say, aspect of all, if you want to come up with something very powerful in the very end. Sure. So one of the biggest challenges in ML, machine learning in general, is how to get some data. Getting some data may not be as easy as possible. Even validating a model using field tests is not a simple task. You may need a lot of funding to employ people to do some validation on the ground. For example, soil moisture, you want to validate on the ground, you may need enough resources to achieve that one. Otherwise, it's not that straightforward to do. It's not that straightforward to do. You may need enough resources, I say, to do that. Say you want to estimate the crops harvested per unit area in kgs or per hectare. To achieve that one, for example, you want to predict the county scale yield using machine learning or using remote sensing observations. That may not be a straightforward job. It may not be a straightforward job. You need enough resources for you to do that, because you need to get enough images. If you are using images to do, say, maybe semantic classification of the entire location, then you have it in 2D, 3D histograms to classify the band time for each bin. You apply maybe deep learning Gaussian process using convolutional neural network architecture, for example. In the end, you may get a very good result depending on, I say, what you get. So that is that. So the challenge is access to data and the validation for data labeling in case of supervised machine learning.
Okay, so this is very, very interesting and also so much exciting. I see we are running much out of time, but I have seen that Hamad is also asking some few questions here.
Yeah, I can answer, no problem. Where I am is 10:43, but I don't care.
Okay.
Yeah,
Yes.
please ask.
So maybe Hamad, you can open your mic so that you can summarize the question very fast, please.
Hello.
Hello.
Yes.
So I have two questions. The first one is related to evaluating the efficiency and capability of machine learning models in a commercial and precision agricultural. So how can the development of machine learning models like for soil moisture, can be optimized to cater to diverse needs of different crops? And to what extent can this model be scaled to be applicable to different geographical regions and farming systems?
Okay, yeah, thank you very much for your question. So to answer that question, in terms of say optimization of the model, say for example, let me take just an example. Suppose you want to create a baseline, say geospatial data set for quantifying agriculture production in maybe Kasarani, for example. Say, how can you do this? You may train some data to predict where crops will be growing based on the satellite information, the satellite data. So what you can do, you may integrate the crop information data. Let me go to this slide. Yeah, so you may get say, for example, the soil characteristics data, the crop information data from agriculture office, if they can give you that data, and add this data to the satellite data. So it means you have images. In addition to the images, you also have the time series data for, say, different aspects or for different locations. You see, some of this may be thematic data, like the soil type is thematic, pH is thematic, say soil moisture content, organic matter, nutrient. If you get that information or the crop information data, you take this data, you combine it with the Earth observation data. Then, in addition to this, if you have data for prices, like the projection in the market, how much they sell particular type of say crops, you may also take that information and integrate it to your model. It means the architecture of that model will be powerful. It won't have gaps. It won't have enough. It won't have more gaps, which will also be say projected into the final output. So you can now implement this one and make the data available to the public, which may be, for example, a food security dashboard. Then how do you collaborate with this one? This may take people or farmers as the end users, or the Department of Agriculture, or maybe other people who are interested in using it to to check some information. One of the most information which can be checked can be maybe agricultural land use. So if you are taking soil characteristics, climate change, agronomic practices, crop information, satellite or the Earth observation data, you are fusing this information. By the end of the day, you can develop a very powerful dashboard which can be able to classify for you the agricultural land use. You may be able to know that, okay, this is agriculture, this is coffee, this is for dairy, this is for pasta, this is for maybe sugar, this is for soybean, this is for tropical fruits, different colors from a given image as seen in an interactive web map. So this information is very, very important for policies and practices which result into a more equitable access to food for a different, say, region. If the goal is to, say, develop something in relation to food, say, security. So by the end of the day, somebody should just log in or check into the system, check whatever they want to check. Are they interested in the soil moisture? If it is only the soil moisture, you may also think, like I said, you may think about the station. You may think of the soil moisture sensor station. If an agricultural department has such information in their farms, a soil moisture sensor station, or do they have, usually most agricultural departments have weather stations. So they also have data for weather. You may also take that data. Already, you can have a background image for any agricultural station. All the farmers, they are planting their crops. You already have a background image. So you may add the data from their labs, the data from their offices, like the data from their weather station, if they can give you. If they have soil moisture sensor stations, or if they use, say, some equipment for soil moisture estimation, you can take their data, which they record in their logbooks. So that information will make the model stronger. And if you want to also think runoff, to think about runoff, instead of thinking about runoff data, if you have some data for maybe, like I said, the evapotranspiration, some UAVs, we can mount the evapotranspiration sensor to a UAV. When it is taking the images, it also grabs a component regarding to that one. So if you come up with a dashboard, in addition to a dashboard, you may also develop an Android app, for example, to achieve some tasks, to advise some farmers for a particular area, to say, okay, what do they want to know? They can know maybe the soil type of a given area by just using a mobile app. Or they may know the soil moisture content. That will assist them to know if it is time to plant a certain type of seed. But to know the best time to plant a certain type of seed, it means the data set which you used in training the model should have a component for that. Otherwise, the model won't be able to give you an output for that. I don't know if we have explained that one better for you.
Yes, thank you so much for this good.
Yeah, thank
for
you.
your answer.
Yeah, thank you.
Okay, so
Questions?
thank you very
Yeah.
much. Thank you very much, Robert, also
Okay.
Ahmad, and the team which has been so patient to listen. And for me, I would love to appreciate the presentation. It has been really incredible. That is really too much information, very much insightful, and I see members are also appreciating. So this is really great, and we appreciate you all. So we would love to be to develop a culture of developing each other, and maybe probably in the near future we are going to be having our members also sharing their work, also sharing their skills and also expertise. So if you are having any great work that you are willing to share with us, you are much welcome. So we can always share through the email, then you will be very much welcome to talk to us. So it's not only the speakers who are here, but also the members are much welcome to share with us. And then before Robert, you leave, I can see some members are also asking for the presentation. I'm not so sure if it is possible that you can share with us for that.
Okay.
Yes.
Okay. Okay. I will do.
All right. So thank you very
Thank you.
much for your kindness, Robert.
Okay. Thank you.
And also I wanted to we were to give some few comments and some of the things that we are planning for the next session. So we are planning to have some workshops, some kind of like just 1 hour or just a few minutes talk session to be guiding or training all our members on the basics of the programming, so that all of us we won't be assuming that everyone knows about the coding, about the Google Earth Engine, but we wanted to do such kind of sessions. And here is when we welcome all of you, because I know most of you have some interaction, some skills, some experience with coding. So you can also get in touch with us so that you can be participating in these sessions. But the plan is not yet mature. We are going to share with you when we have set everything ready. I Michael has just left the meeting. Then Christopher is not around with us, so I won't give them time to share with us because they are not available. But thank you very much, everyone, for being patient to this far. Thank you so much, Robert, for your kindness to come to speak with us despite it being so late at your end. So we are grateful. And we also apologize for the issue of the recording. Bruno, I did note your text, but on our side the recording part is unavailable. I don't know how we can get it on, but I'm going to look into that so that in next session we can have all our sessions recorded. It really helps for us. So we are going to look into that and see how best we can have everything recorded for the benefit of the community. Thank you so much. And without much ado, I would say we are going to close the meeting. Or anyone has anything? All right. I don't see there is anyone with anything to mention, but we are going to close the session and we are going to mention to you the next session that we are going to have. As you have heard, I've said that we are planning for those weekly hands-on programming basics in the GE. So we are setting up that, and it's going to come up immediately. We are finalized in everything that we are setting up for that. So you are also welcome. We can be giving you some few things, some small topic, and you can lead in that. So it will be a community thing, not for us alone. So you are also welcome. So if at all you would love to share with us, you will be much welcome to be taking